In 4.1 Aqueous Solutions, we're going to start to think about what does it look like when we dissolve a compound in water and what happens when the reaction occurs in water. So an aqueous reaction, we've seen these before as a subscript AQ in a reaction. And so when we start to think about that, we can have this. But here, there are a bunch of different definitions of the parts of things that we're going to think about. So when we react something in water, the solvent is the substance doing the dissolving. So a lot of times this could be water. So in an aqueous solution, it is definitely water. This could also be in some organic solutions. It could be some other type of solvent or an organic solvent. Most of these, if you hang around in chemistry until organic 2, you'll see these. They are substances like dichloromethane, or ether. It's not really important what those are, but basically when we think about an aqueous reaction or any other reaction, the solvent is the substance doing the dissolving. The solute is the substance that dissolves. So we know that that could be something as simple as sodium chloride. So we know that you can dissolve salt in water. We can think about, you could dissolve sugar or any other solid that when you mix it with water, it dissolves. So the next thing we want to think about are homogeneous versus heterogeneous mixtures. So when we think about a homogeneous or homogeneous, this basically tells us that, the solution is fully dissolved. So what this means is when you have your beaker, in this case we're going to fill it with water, you're going to add your components. We will add something green, you add solid. Eventually, over time, you should end up with a new beaker with water in it, where your substance cannot be separated. So separated by filtration. So when we think about a heterogeneous mixture, so this tells us that the solution is not fully dissolved. So what is that? In the South, sweet tea is a big thing, right? So we know, or maybe you don't, if you order tea in perhaps the other part of the countries, they will ask you to add your sugar yourself. So in this case, we will have green sweet tea, and you are going to add yellow sugar cubes. So in a heterogeneous mixture, what we're actually going to see is something very different. Over time, we're going to get our glass back, and we're going to have something with some amount of dissolved, but we're also going to have something at the bottom. So in this case, in our sweet tea event, we have undissolved sugar. And so what this tells us is that we could separate. The two components. The other thing that we'll start to see is that this has to also do with the solubility. And we're going to talk more about what solubility is, what it looks like, how do we use it in the 4.2 precipitation reactions video. So we're just going to say coming soon. So the other things we're going to think about are electrolytes and non-electrolytes. So we know that electrolytes are a thing if you drink some sort of sports drinks, such as Gatorade or Powerade or Smart Water or anything like that. So an electrolyte is a substance that dissolves into its ions. So this could be something like NaCl, KCl, etc. A non-electrolyte is a substance that does not dissolve into ions. So it does mean it goes into solution. It just doesn't separate. So these are things like sugar. If you dissolve methanol, CH4, into water, or you create a mixture, we will see these as non-electrolytes. So what does it mean for something to be solvated? So water has the structure H2O, or the chemical formula. So when we were to draw water, and today I'm going to show you the structure, which looks like this. And it has these two lone pairs. So we are going to learn how to draw this in chapter 8 and 9. So today we're just going to think about it. So water has a delta minus and a delta plus. So this is called a delta symbol, and it means partial. So partial basically tells you it's not a fully negative charge, so it's not an ion, but it's not a fully positive charge either. So the partial charges allow for solvation. So what does that mean? Basically, if we were to have a sodium chloride, so we're going to have Na plus and over here Cl minus, and we want these to be solvated by water. We need them to dissolve. But a negative or a positive charge doesn't really want to be there alone. So in this case, we're going to have the water structures where the delta minus is surround the sodium ion. And over here, we're going to have the opposite orientation for these waters, to where the delta plus surrounds the chlorides. So the ions are surrounded by the polar water molecules. We see this a lot we see this in proteins, we see this in other compounds in biological systems, that water allows for ions and molecules to be solvated. So what happens if it's a molecule? So let's just say we have methane, CH4. It doesn't have any charges. So these CH4 molecules, which in this case I will make as red circles, and we will make our water molecules blue. So in this case, we have our red circles in our beaker, and our water molecules just kind of hang around. If it is a molecule, there is no interaction. If it is a molecule, the water, that's not how you spell that. The water and water and molecule do not interact. So in this case, we have different solvations, whether it's an ion or a molecule. So the strength of an electrolyte. So not all compounds dissolve well. We talked about this a little bit with the sweet tea, or when you have regular tea and you try to make it into sweet tea. So the question becomes, what does that mean? And so a strong electrolyte dissolves completely into its ions. So these are salts. These are salts. These are other types of components. So a weak electrolyte dissolves partially into its ions. So in addition to salts, we could have things like strong acids or bases. A weak electrolyte, these are slightly soluble components, or weak acids and bases. For the most part in Gen Chem 1, we are going to deal with strong electrolytes, things that completely dissolve. They will either completely dissolve or not dissolve at all. So in this case, let's think about what quantity and what ions you would find in these solutions. So what does that mean? How do they break apart? What do they look like when they get there? So you should be able to look at some of these components and say like, oh, well, it breaks into two parts. So in this case, you're going to have 2 aluminum, 3+, and 3 sulfate ions. So if you remember back to the polyatomic ion table we met in chapter 2, and the periodic table, which is like our best friend, we'll be able to see those components. So for potassium chloride, that's going to dissolve into 1 K+ and 1 Ci- when it dissolves in solution. So what about sodium phosphate? So we're going to get 3 Na+ and 1 PO4 3-. So when we look at CH4, that's not an ionic compound. So what we get in solution is in fact CH4. So this is a non-ionic compound. And so if we look at C6H12O6, you're probably like, I don't even know what that is. But what we do know is that it doesn't dissolve. So we'll say that no ions are created. So in this case, what ions we see in solution are basically what breaks apart. So the next thing we kind of want to start to think about is like, what are the solutions? So a solution is basically a beaker with water and something dissolved. So what does that really mean? So thus far in Gen Chem 1, we've talked a lot about, we added 5 grams of this and 12 grams of that in water, and now what happens? So we want to now be able to say we added 15 mils of a solution. So the concentration of a solution is molarity, which is a big M, and this is equal to moles divided by liter. This is kind of similar to density, but it is a more standard environment. So how can we do these calculations? So we are going to calculate it by, we have a molarity divided by a volume. So this we're going to convert to moles. And this we need to convert to liters. So we're going to start with the mass. So we're going to take our 23.4 grams of sodium sulfate. We're going to use the molecular weight, which is 142.05 grams and 1 mole of sodium sulfate. When we plug this in our calculator, we get 0.165 moles of sodium sulfate. Okay, so now we need to convert to liters. Sorry. So we're going to take our 125 milliliters. There are 1,000 milliliters in 1 liter, and that gives us 0.125 liters. So to calculate the molarity, it's going to be 0.165 moles divided by 0.125 liters. When we plug this in, we're going to get 1.32 molar sodium sulfate. So don't forget, significant figures come from the problem. So in this case, we had 3 in both of our answers, so there are 3 in this. So molarity is just the ability to give a concentration. So let's do another example. So in this case, we want to know what is the molarity of a solution where 3.86 grams of sucrose, here's the formula, is dissolved in 275 mils of water. So we need to determine the moles divided by liters. So first we'll determine the moles. We're going to take our 3.68 grams of sucrose, C12H22O11. And the molecular weight of that is 342.34 grams and 1 mole of C12H22O11. And so this is going to give us 0.0107 moles of C12H22O11. And the volume, so we're going to take our 275.0 milliliters. There are 1,000 milliliters in 1 liter, and that gives us 0.2750 liters. So now let's determine the molarity. So we're going to take our 0.0107 mole divided by 0.2750 liters, and that gives us 0.0391 molar. Or if you wanted to report this as millimolar, that would be in 1 mole, there are 1,000 millimoles, and that would be 339.1 millimolar. So be sure both of these answers are somewhat equivalent. For an exam or a question that I give you, make sure it looks for the units, and in this case it just says molarity, so that in fact is moles per liter, 7 molar. So let's think about the concentration of an ion. So a lot of times we need to think about, what does this mean? So if we have 1 molar, that means that we have 1 mole in 1 liter. So when we think about this component, it is 1 mole per liter of everything in solution. So when we think about this question, so if we have 1 molar sodium chloride, this is going to be, it's going to break into the sodium plus and the Cl minus. So those are the ions, but the question becomes, what are they? So if it is 1 mole per liter sodium chloride, the concentration of each ion is going to be 1 molar sodium and 1 molar chlorine ions. So how does this come to be? So let's take a step back and think about, what does it mean to be sodium chloride? So each sodium chloride is composed of 1 sodium ion plus 1 chlorine ion. And so if the concentration is, so if we have 1 mole of this, we have 1 mole of sodium and 1 mole of chlorine. So the concentration will be the same. So let's use that information and think about sodium sulfate. So the sodium sulfate breaks into 2 sodium and 1 sulfate ion. So now we have to think about what the concentration is. So the concentration of the sodium ions is going to be 2.00 molar sodium ion and 1.00 molar sulfate ion. Now you're probably like, I don't understand what happened. So this 2 plus in the sodium ion means that for every mole of sodium sulfate, so a sodium sulfate breaks apart into 2 sodium plus 1 sulfate. So if we have 1 mole of this, it breaks down into 2 moles plus 1 mole. Now, I know that this seems a little bit weird, but when we've talked about the mass percent, we know that there are 2 sodium and 1 sulfate ion. So let's do something that's not 1 molar. So for our potassium chloride, this breaks down into potassium and chloride ions. So we have 1 molar, we have 0.21 molar potassium and 0.21 molar chlorine ions. So our last one down here is molar 0.677 molar magnesium sulfate. So this is going to break down into magnesium 2 plus and the sulfate ion. So the magnesium concentration will be 0.677 molar. And the sulfate ion will also be 0.67. So the concentration of each ion is based on the concentration that it starts with. So if we calculate how much molarity something is, we want to start to think about how can we use these calculations. So instead of just calculating the ions over and over again, what about if we used it and we wanted to know how many moles of HNO3 are in 2 liters of 0.2 molar HNO3? So in this case, we're going to use the molarity at very similar to how we have for density. So it's going to be 0.200 molar, and that equals 0.200 moles divided by 1 liter. So what did I do here? I split the units. So if molar equals moles divided by liter, that is all I've done. I just took the molarity and I broke it out into units that I can use for a unit conversion. So in this case, we now have our molarity and we want to multiply it by the liters. So we're going to multiply by 2.00 liters. So our liters will cancel and we'll be left with molarity or moles, which is 0.400 moles of HNO3. So molarity can be split apart. 1 molar equals 1 mole per 1 liter. And so you can split this out in any way you want. So in our next question, it asks, how many grams of sodium sulfate are required to make 0.350 liters of half molar sodium sulfate? So we're going to take our 0.500 molar, which equals 0.500 moles in 1 liter, multiplied by 0.350 liters, which gives us 0.175 moles of sodium sulfate. Now it asks for grams, so we can take our 0.175 moles of sodium sulfate multiplied by, in 1 mole, there are 142.06 grams of sodium sulfate, which gives us 24.86 grams. If we look at our problem, all of our starting values only have 3 sig figs, so we will get 24.9 grams. So molarity can be used in calculations. It can also be used in other ways. So this question is a little bit more complex. And so in this question, it's going to start to ask something that's a little bit more advanced. So it wants to know, what is the concentration of sodium ions in a solution created by mixing 75 mils of 1.35 molar sodium chloride with 125 mils of 0.732 molar sodium sulfate. So now we're going to combine all of the things that we need. So we need to figure out, so the plan here is we want to figure out the molarity is equal to moles divided by liters. So of the total solution. So we mix two solutions. So the volume is going to be 75 milliliters plus 125 milliliters, which gives us 200 mils. When we convert to liters, that's going to give us 0.2 liters. So that's good. But now we need to determine the moles of sodium. So for sodium chloride, we have 1.35 molar NaCl, which is equal to 1.35 moles of NaCl in 1 liter, but we only have 0.075 liters. And this gives us 0.10125 moles of NaCl. Now we need to figure out how many moles of sodium are in this value. So we're going to take our 0.10125 moles of NaCl, and we're going to convert that to just sodium. So for every 1 mole of NaCl, we have 1 mole of sodium plus, which just gives us 0.10125 mole Na plus. So now let's look at the 125 mils of 0.732 molar sodium sulfate. So for sodium sulfate, we're going to repeat this process. So we're going to take 0.732 molar Na2SO4, which equals 0.732 moles in 1 liter. We are going to use 125 mils, which is 0.125 liters, which gives us 0.09185 moles of sodium sulfate. So now we need to figure out the number of sodium ions in this number of moles. So we're going to take our 0.091875 moles of sodium sulfate. For every 1 sodium sulfate, there are 2 moles of sodium plus, and that gives us 0.18375 moles of Na plus. So the molarity is still moles divided by liters. So in this case, we're going to take our 2 sodium moles, 0.10125 plus 0.18375 divided by 0.200 liters, which is 0.285 divided by 0.200 liters. So when you plug this into your calculator, you should get 1.425 molar. And if we use significant figures, it's 1.43 molar sodium plus. So when we look at this example, the important part here is to think about, we need to determine the number of moles of sodium ions, and then we need to determine the total volume. So we'll try to get that backed out to where you guys could actually see it in this way.